Okay, I hope you are all able to see my screen. Can someone message in the chat if you are able to see and see the screen and hear me? Yeah. Okay. All right. So in the previous lecture, we were looking at pointers. I said that when you pass a variable to a function, the function actually makes a copy of it and then modifies only the copy, not the original, right? So when you leave the function, whatever modifications you made to the copy, they will be invisible to the original. The original remains the same. But suppose you want to modify the original through a function, then rather than passing the variable, you have to pass its address. Okay? Any function, whatever data given to it, the function makes a copy of it. So if you give the variable, the function makes a copy of the variable. If you give its address, the function makes a copy of the address. All right? So through the copy of the address of the variable, we can still access the original variable, right? So that is what a pointer does. Okay, so a pointer allows us to share information between two functions without making a copy of the information. Okay, so that is one way of sharing information. The other way is to actually share the data itself, but then you make copies of the data and then deal with these copies and you send these copies back and forth. So I want you to sort of what do we say, square a number. I give you this number, you make a copy of it, you square it and give the result back to me, and then I override my data with the data you give me. So it's like a lot of copies are going back and forth, right? That is one way, but that is too tedious, right? Rather than that, we will have original data at which uh, more than one pointer will be pointing to. So I will share the address of my data to you. Okay, the data will not be copied. There is only one copy of the data, master copy, but there are many handles to access this data. Those are pointers. Okay, so we are all sharing the same data, the same copy. We are all looking at the same copy. So any modification done by you is also visible to me, and any modification done by me will also be visible to you. Okay, so this is another way of sharing the data. So we are all accessing the same data without making copies. That is through pointers. Another way is we actually make copies of the data, send back and forth. I send you the data, you make some changes, you send it back to me, I make some changes, send it back to you. So this is too much of copying the data. All right. Now you may say, okay, how does it matter if it is just integer or char or float, whatever it is, small size data, right? So it doesn't matter even if we copy them and send them back and forth. It should not be a matter. Yes, sort of, it is not a problem then. But what if you are dealing with large size data? For instance, say an array of size 1 million, 1 million integers, right? Now, it is absolutely inefficient to make a copy of this array, send it to you, you making some modifications to it, sending it back to me, and I copying it back into my original array, right? So that is a very bad way of doing it, right? So when you have large data, rather than making multiple copies of it, passing copies of its addresses is a much better method, right? So the address for the entire array or the address for a single variable, both are of same size. Whether you have a pointer to a single variable like an integer, that pointer size is 4 bytes, or if you have a pointer pointing to an entire array of 1 million integers, that pointer size is also 4 bytes, right? So here, rather than sharing an array of 1 million integers, making a copy of it, you just share the pointer or the address to the first element of the array. So you are making a copy only of 4 bytes, not 1 million into 4 bytes, right? So that is one very important use case for pointers. All right. Another application of pointers is, say, when you want to deal with dynamic memory or dynamic data, right? For instance, suppose your data is the size of your data is never constant. It is either constantly growing or decreasing, or constantly being modified. For instance, say you have an array. Now imagine you want to add even one element to the array. You cannot add just one element to the array. You have to create, suppose your array has n elements. Okay, now you want to add one more element. So you can't add just one cell to the array. You have to create a new array of size n plus 1, copy all the previous n elements from the previous array to the new array. Okay, now imagine if your n is million, what a hectic task it would be to copy all the million elements from the previous array to the new array. And just for one element, one extra element, you have created an entire array of 1 million elements, right? So that is too much of wastage of time and space, right? So a better way would be to use something called linked lists. We will not cover linked lists in this course. We don't have time. You will look at them in the data structures course. But linked lists are not a contiguous memory location in the RAM. Okay, it is like I have some space here, I have some other space there, some other space somewhere else. So I keep connecting these spaces using pointers, and wherever I get a space, I utilize that to store a new element. Okay, so in this way, using these non-contiguous spaces in the RAM, I can keep growing my linked list size or remove a node. Linked list is made up of nodes. Each element is called a node in a linked list. So I can add a node, delete a node, right? Swap the nodes. I can do any kind of modifications to linked list at a much faster rate using much lesser space compared to array. Okay, much lesser space when you are trying to make a copy. In a linked list, when you want to add one element, you need to add only one node. You need not create an entire copy of the previous linked list and then add to that. Okay, so these are various advantages of pointers. So you can deal with linked lists, trees, heaps, stacks, queues, graphs, all these things using pointers. Whenever your data is constantly changing, the best way is to use linked lists rather than arrays. Okay, so these are two main applications of pointers. One is sharing the data across functions. Second is it is useful in dealing with complex data structures like linked list, trees, graphs, etc. All right, so these are multiple uses of pointers. So we saw some examples of pointers, functions which have pointers as arguments, right? We looked at square function without pointer and with pointer. So when you pass values as arguments, it is called call by value. When you pass pointer as argument, it is called call by reference. All right. So I won't again spend much time on that. We discussed in the previous lecture. Yeah. So let's continue. So in the last lecture, we looked at incrementing a pointer, right? Suppose I have int x equal to 5 and say int star p equal to ampersand x. So what does it mean? Suppose I have some cell with value 5, x has a value 5 and it is stored at some location, say 200. Okay, which means p is pointing to x. All right, when p is equal to 200 and 200 is the address of x, what it means is p is pointing to x, this location. Okay, now I asked you, what if I do star p plus plus? Okay, so last time I asked you, let me unmute. Yeah, so can anyone tell me what will happen when I do star p plus plus? You can unmute and speak. Yeah, hello.
The value will be added by 1, sir.
Which value?
The x 5 will become 6.
Exactly. Good. So when I do star p plus plus, what will happen? Star p is nothing but x. So this is equivalent to x plus plus. Okay. So x will be overridden with 6. Okay. Now suppose I do p plus plus, what will happen then? Yeah. Can anyone tell me? If I do p plus
Sir,
plus, what will happen?
sir, the address will get
Hmm.
incremented by one data type size, sir.
Exactly. Very good. So p plus plus means p equal to p plus 1, but this 1 is not 1 byte. It is one element of the current data type. Since p is pointing to integer, okay, p is an integer pointer, it will be incremented by one integer size. Okay. So this is equivalent to p plus 1 into size of int. Okay, that is nothing but p plus 4. Okay, so here 4, or this size of whatever data type you have, that is called the scale factor, right? So here p becomes, anyway, yeah, so when I do p plus plus, now p will become plus 1 means plus 4 bytes. So p will become 204. Okay, so there will be some other cell with 204 address, and we don't know what data it has. Okay, some random data it has, we don't know, that is outside the program memory. All right.
Sir,
Yeah,
sir, so I mean, adding this P to 1 will add the address of that P, sir. Then,
it will increment p by the size of the data type.
okay. So, can we directly do this like 200 plus 1 into 4?
Yeah, we can, but we don't know if it is 200 or something, it is some big number.
Okay. But
So
so this 200 is the space,
address,
address which our pointer is pointing to, right? So 6 is the integer and this 200 is the address of that integer, right?
exactly.
Okay, so got it.
Yeah, so this 200 or whatever, this number is not visible to us, we deal only with p. So whatever we want to do, we do with p only. P plus plus, p minus minus, p equal to p plus 5, whatever we want, we will do with p only. It will automatically increase p by so much value. Okay. Yeah, so let's just quickly see a case. So int x equal to 5, int star p equal to ampersand x. Okay, now I say value of x is d. Okay, and the value of star p. So I'm just trying to print every possible case as detailed as possible, and then the value of p is this, and the address of x is ampersand x. Okay, so first let's print this. Okay, when I say value of x, what will it print?
Why, sir?
Yeah, next when I say value of star p, what will it print?
Some address of that value, whatever address is there for 5, it will be printed.
No, it will print 5.
Exactly, it will print 5. Star p is 5, p is the address, this is the address of x. Okay, and this will also be the address of x. Okay, so last two values will be equal, and then first two values will be equal. Okay, So first two statements will print 5. Next two statements will print address of x. So you can print address of x either using ampersand x or p. Okay. When you do star p, it will dereference the address and print the value there. When you do ampersand x, it will reference you the reference of x or the address of x. Okay. Let's see. These are warnings. You can, okay, instead of %d, when you are printing p, use %u. Even then it will give a warning, but ignore that warning for now. Only when you're printing pointer address, use %u. Okay. Otherwise, you are printing star p or x. Anyway, you use %d. That is fine. These are warnings. Ignore them. Oh, oh, did I give percentage before value? Okay, that's the problem. Okay. Okay. Yeah, you see, value of x is 5, value of star p is also 5 because x is stored at p, and when you say star p, it will access x. And value of p is some address, and the address of x is the same thing. Okay, p and x both have the same value. I mean, p and ampersand x, sorry, p and ampersand x both have the same value because p is nothing but address of x. All right. Okay. Now,
Sir?
yeah.
The address it creates is a random garbage.
Sorry.
The address it a random garbage value, right?
Address which it creates, you are saying address of x.
Like the P, sir. Yes, sir. Address of X.
No, it is not random. X is somewhere stored in the memory. No, that address it will store in P. In the memory, every location has an address. If you don't assign X, if you don't assign the address of X to P, and then if you try to print P, then it will print some garbage value. But here, I have assigned address of X to P, no?
Yes, sir.
Suppose if I don't do this, suppose if I remove this, okay, I say int star P. Now I try to print value of P and I also try to print value of star P. It will print some garbage value in both the cases. Okay. Yeah. You see star P, it's saying 1. We don't know where 1 came from. I didn't initiate any variable to 1, but it is printing star P to be 1. And what is P? Some address. I don't know what that address is. And that address is different from the address of X. Right? X address is ending with
Yes.
364. This is ending with 608. Both are different addresses. And at this address, it seems value 1 is there. So we don't know what value will be there at that address. So it will print anything. That is the difference. But in the previous case, I actually initialized star P to the address of X. So it will be pointing to address of X. Okay.
Yes, sir.
Now, yeah. Now I will increase P, I mean star P. Okay, now I print the value of X and star P. Now what will it print? Now what will X be?
Six,
Right, and what will star P be?
6, sir.
Good. Yeah, that's it. Star P is nothing but X. So this statement is equivalent to X plus plus. Okay, so X will become 6, and since P is still pointing to that location only, star P will also be 6. So let's print this. Yeah, you see now X is 6 and star P is also 6. Okay. Okay, this I need to use %u address of X. Let me change this also. Okay, let me it now. Yeah, so you see initially X is 5, star P is 5, address of P is this, address of X is also same thing. Okay, after that I did star P plus plus, then X became 6, star P also became 6. Okay, now I will do P plus plus. Okay, Now what will these values be? X will be what will X be?
Five, sir.
It will be the 6.
Yeah, it will be 6. It is not modified. I did only p plus plus, so pointer is incremented. X is unchanged. X will be 6, and then star p will be
6. Uh, it
The
doesn't have
address
any
is in.
value.
sorry.
The address of P is changed to some other variable which we haven't assigned.
Right. So star p will be some
6
random value.
1 6.
No, it is not pointing to X anymore, right? So let me print the address of P, or the value of P. Value of P is address of integer next to X, right? Initially P was pointing to X. Now you did P plus plus. So what will it do? It will change its address to next integer. It will increase by 1 integer. It will point to the next location. Okay. So when you say P, it will print that address, not the address of X. And when you do star P, it will try to print the value in that location which is next to X. Okay. Random value which is next to X. We don't know what that is. Fine. Let's okay, just warnings, ignore them. Yeah, you see, after this value of star p is 6, what did I do? I did p plus plus. Okay, then X is not changed. X is still 6 only. Since I did p plus plus, p increased by 4. You see, earlier p was ending with 956. Okay, now p's address became 960. Fine. Now value of star p is the value at this address. In this case, it is printing same thing. You see, we don't know what it will print. Sometimes there is nothing stored there, or the same address is stored there, or some other value is stored there. It can print anything. In the previous case, it printed 1 at some address. In this case, it is printing the address again when you are trying to print the value at that address. So there is no logic to what it will print. All that you need to understand is it is now not pointing to X, it is pointing to the next integer, and you can see the difference in the number of bytes between new P and the old P. Old P and new P, there is a difference of 4 bytes. Okay, and the new P, we don't know where it is pointing to and what value is there at that location. Fine, there is a difference. Okay, now suppose I do P minus minus. All right, now what will star P be? Anyone tell me? Suppose I decrement P again. I incremented P. Now I decrement it. What will be star P? What will P be?
6.
Right. Yeah, that's it. P will be pointing back at X.
ఇప్పుడు ఒకసారి వాట్సాప్ లో ఛార్జింగ్ పెట్టి ఛార్జింగ్ పెట్టి
Okay. Sriram Reddy, Abhiram Kartikeya. You are getting absent for the entire course. I hope you are able to see my screen. Okay. All right. So let's print it. Yeah, you see now again star P is 6. Okay. That's it. If I print address of P, it will again print the address of X. Yeah, you see, this is 4428. The previous address of X is 4428. When I did P plus plus, it became 4432. And then I did P minus minus, it became 4428. Okay, so that is the difference. Fine. All right. Okay, so let me do one thing. Okay, now so we are done with that. All right, so this we did. Now imagine, by the way, I hope you are able to hear me and see the screen, right? I hope there is no problem there. Can anyone just
Yes, sir.
reply? Yeah, okay, fine. Okay. So now imagine we are pointing at an array. Okay, so suppose I want to create a pointer to an array, not one integer, one character, but I want a pointer to point at an entire array. So what I do, suppose I say some array, okay, a of 4 equal to 1, 2, 3, 4. So how will it look? 1, 2, 3, 4. And imagine their addresses are 200, 204, 208, 212. Okay, now I create a pointer and I give the address of the first element of A to this pointer. So what will that pointer look like? That pointer will be pointing to this location, right? Because P's value will be 200. Fine. Now suppose I do P equal to P plus 2. Now can someone tell me what P's new value will be? What will be P's new value?
206.
Why 206?
208.
Yeah, it's 208, right? Why? When I say P equal to P plus 2, that is equivalent to saying P plus 2 into size of int. Yeah. So that is P plus 8 and P is 200. Okay. So it will be 208, right? So what does it mean? It means P will be now pointing to this location, right? Because P is 208. Yes. Okay. So before this increment statement, if I had printed star P, what will it print? If I have printed star P here, what will it print? Come on, quickly.
Three.
No, before this statement.
1.
1.
Ah, good. Yes, 1. After this statement?
3.
Yes, that's it. Right? So before I incremented P by 2 places, if I printed star P, P was pointing to the first element of the array. So star P will be first element of the array, that is 1. Okay. And then I incremented P by 2 places or 2 integers. Fine. Now if I print star P, it will print the third integer in the array, that is 3. All right. Now the same thing, rather than using these two statements, I can use a single statement. Can someone tell me what that statement will be? Print. what the statement will be? Can I combine these two into one statement? Can you think?
Star of p plus 2.
Very good. Star of p plus 2. This will also print 3 only. This will also print the address located in p plus 2. P plus 2 is 208. So star of 208 is 3. Right? So here p is not updated. You're directly printing star of p plus 2. P plus 2 is 208. Yeah, someone's mic is on. Can you please mute? Star of 208 is 3. Okay. So in this case, P is pointing to this location only. Okay. But when you say P plus 2, that is pointing to this location. P plus 1 will be pointing to this location. P plus 3 will be pointing to this location. So when you say star P, it will print 1. When you say star of P plus 1, it will print 2. Star of P plus 2 will print 3. Star of P plus 3 will print 4. Okay. So can you guess this is looking similar to there? This is equivalent to, in terms of array indexing, this can be expressed in a different way. When I say star of p plus I, okay, so first let me say star of p plus 2 is what? P of 2. Star of p plus 1 is their equivalent to p of 1. Similarly, star of p plus I is equivalent to p of I, and star of p plus 0 is equivalent to p of 0. But in other sense, this is nothing but star p. So p of 0 is nothing but star p, which means p is nothing but the pointer to the first element of the array. But you see, this is true for even the array name. This is true even for the array name A. So what did we understand? A is nothing but a pointer to the address of the first element of the array. Okay, so now instead of P, you can use A directly. So you can, so rather than saying A of 1, A of 2, etc., you can also use star of A plus 1, or A of 3 is nothing but star of A plus 3, and A of 0 is nothing but star of A plus 0. Okay, and if you solve this equation, what will you get? Star of A. That's it. So A is also nothing but a pointer. So whatever arrays we have been using so far, they are nothing but pointers. And I hope now you understand why the indexing of an array starts from 0 and not 1, because of this reason. Okay, because of this, this is the reason why the indexing of an array starts from 0 and not 1. Okay, because A is pointing to the very first element of the array, so star A should give you the first element, and star A is nothing but star of A plus 0, so you write A of 0 as the first element. Okay, the moment you say A of 1, you are adding 1 to the pointer, which means you are accessing not the current integer but the next integer, so that will give you the second element. That is why A of 1 points to the second element. Okay, got it? So that is the difference. Fine. So you can play with pointers now, but you cannot do something like this, A plus plus. This will give an error because A is a constant. Okay, A is a const variable. What do we say? Const variable, and hence cannot be changed. Okay, you can access A of 1, A of 2, A of 3, but you cannot change A itself to be A of 1, A of 2, like that, address of A of 1, A of 2. Whereas if you have a separate pointer pointing to A, that pointer you can update any way you want. You can do P plus plus, P minus minus, and so on. But A itself you cannot update because you will lose the very first address of the array. Okay, so A always has to point to the first element of the array. Otherwise, you will lose access to A. You can always create a new pointer pointing to first element, third element, fifth element, etc. You can play with that pointer, but you cannot modify A itself. Okay, so now you understand, when we pass an array to a function, we are not passing the copy of the array, we are passing the pointer to the array. All right, so suppose I have some function like say sort array. Okay, and I'm passing an integer array and size of the array, whatever it is. Okay, and I'll have some code which sorts the array. Here what you need to understand is, I am not passing all the elements of the array. The function is not creating copy of the all the elements and then sorting that copy. No, I am passing only the address of the first element of the array. So this is same as let me remove this. This, or I can also say address of A of 0. That is also A only, right? Or I can also say int star p, because A is nothing but a pointer to array. I can also say int star A. Okay, all these are equivalent. Okay, so you are basically passing the pointer to the array, but even though you're passing the pointer, whether that pointer is original array name or some pointer pointing to the first element of the array, it does not matter. Either you can use the original array name to access the elements, or you can use a pointer name to access the array elements. Like I said here, here array name is A. Okay, so to access any of these elements, you can either use A of I, or P is pointing to the first element. You can also use P of I. Okay, so you can pass either A or P to the function, and you can access any of the elements in the array. Okay, both are addresses of these elements. Elements are, there is only one copy of the elements, but you are passing address of the first element, either A or P. Both are pointing to this element only, and then you can access all the remaining elements either using A or P in the same format, A of I or P of I. Okay, so that is how arrays are used in functions. Okay, otherwise what will happen if we have to create a copy of the array? Suppose the array size is 1 million, then the function has to create a copy of 1 million elements, modify whatever changes you want to make to that copy, and then copy back this modified array to the original array. That is too much of headache, right? That is too inefficient also and too time consuming. So although I didn't tell you earlier, normal variables like int, float, char, etc., when you pass them to a function, it creates a copy of them. But when you pass an array, it does not create a copy of the array. It only passes the address of the first element of the array. Okay, so arrays are passed using pointers. They are not passed in the regular sense. So arrays are always passed by reference, not by value. Okay, so I can say arrays are always passed using call by reference, not call by value. Okay, that is the difference. Okay, fine. So arrays are done. So I hope you understood how arrays work with pointers. Fine. And now, although we won't cover linked lists in this lecture, but we need to understand how pointers can be used to create. Yeah, someone has unmuted their mic. Can you please mute? Okay. Devineni Kushal, you're also getting absent for the entire course. Yeah. Okay. So yeah, we need to understand how pointers can be used to allocate whatever memory we want at whatever whenever we want. All right, because pointers are mainly used for dynamic memory purposes. Okay, so there is something called dynamic memory allocation. Okay, so right now you will understand this a little better when we get into structs in the next week. Okay, suppose a struct is, just to put it simply, a struct is a data structure which is a combination of multiple data types. Like I can group maybe 2-3 integers, one string, and one float, one double. All these things I can group into one structure called a struct, and I can use this struct itself as a new data type. Okay, so this new data type will have some size, right? And you can have an array of such data type. You can have pointer to such a data type. All these things, fine. But this data type size will not be a normal int or float or double like that. It will be a sum of a sum of all the number of data types it has and the amount of data it has. Okay, suppose if this struct has 2 integers plus 3 characters plus 1 float. Okay, so what will its size be? This is 4 bytes. Int is 4 bytes, right? So this will be 8 plus 3 plus 4. All right, so this will be total 15 bytes. So here the size of the struct will be 15 bytes. All right, so whenever I want to store a struct, what I should do, I should allocate 15 bytes in my memory and store struct there. So a linked node, a node in the linked list is basically a struct or a structure. You will understand this better in the next lecture. So the simple thing is, I want not one particular data type size, I want arbitrary data type size, okay, and I want memory to be allocated for that. All right, so I want memory to be allocated for that. So there is a function called malloc. All right, there's a function called malloc, which when you give number of bytes to it, how many bytes you want to allocate, it will store, it will reserve that much portion of memory in the RAM and returns a pointer to that location in the RAM. Okay. Now, you see, I don't know what kind of elements I may want to store beforehand, right? Malloc doesn't know. That memory you may want to use to store integers, or you may want to use to store characters or floats or doubles or structs. All right. So by definition, malloc basically returns a void star, void pointer. Okay. What we have to do, once we know the kind of data we want to store in this space, we convert that memory, that pointer, into the kind of pointer we want. So one example is, suppose I want to create an array of 5 integers. Fine. Now what I say, int star p equal to, since, okay, first I will say malloc, I want to create space for 5 integers, right? So I'll say 5 into size of int, right? Now this malloc will return the first address of this block, but that block, it doesn't know what is the data type. So you have to tell this pointer, you convert this pointer into integer pointer. So you use the conversion method here. Okay. So this void star, you are converting to int star. Suppose if you want to store a character array, okay, say character pointer, what you do, you say char star. Suppose I want 8 characters, then I say 8 into size of char. Okay. Now within this, I can access, now I can say, after I do this, okay, suppose I take this, I can say p of 0 equal to 5, p of 1 equal to 20, whatever it is. Now it is like an array. Okay. Similarly, this one, I have character, I can say ch ptr 0 equal to a, ch ptr 1 equal to b, whatever it is. Okay. So I reserved some space in my RAM, but this space is there in some memory called heap memory. This is different from the stack memory which we use for functions. Okay, you need not worry about that now, but just understand this is different from stack memory. It is from the stack memory that some space is allocated by malloc. Okay, so basically we have a lot of flexibility in deciding how much space we want, how we want to divide this space, okay, and then access this space. And then once our job is done, we can also deallocate this space. We can free up this space using a function called free. Okay, so once your job with pointer is done, all these things are done. Okay, you stored something, you sorted them, you did whatever you want. After that, you release this space. Okay, so the command for that is free pointer. Okay, so we can free this pointer whenever we want. All right. Yeah. Any doubt?
Like if we function, it reset the address of the.
Your voice is breaking a lot.
Hello.
Yeah. Repeat.
Sir, if the free function, will it reset the address of the point?
Yeah, exactly. Good. So what it will do, it will reset the address of the pointer. It will make pointer equal to null. Okay. So now pointer will not be pointing to any location. It is pointing to some predefined value called null. Okay. So there are two things. One is void pointer. Okay. I say void star PTR. Another is some pointer's value being initialized to null. It can be int star or void star or char star. So null is the value that a pointer can take. Basically what it says is pointer is pointing to nothing. All right. Void star pointer, what it is saying is not speaking of the value. It is basically saying that I don't know what this pointer data type is. All right. Both these cases, if you try to dereference that pointer, it will give an error, but for different reasons. Okay. If I say, okay, I say void star P1, here I say int star P2 equal to null. Okay. Now, suppose I can say void star P1 equal to ampersand X. It doesn't matter. I can say int X equal to 10. And I can say void star P1 equal to ampersand X. But still, if I try to do star P1, it will give an error because it doesn't know what it is pointing to. It doesn't know how much, when it dereferences, what is the size of the data type and how much it should take. Okay, from the current address, how many bytes it should take, it does not know. Only if it knows, okay, it's pointing to an integer, from the current address, it takes 4 bytes. If it is pointing to a character, from the current address, it takes 1 byte. But if it does not know what it is pointing to, if it is void pointer, it does not know when you dereference it. Okay, so star P1 will give an error because it does not know the data type it is pointing to. Star P2 will also give an error because there is nothing it is pointing to. There is no data at all where it is pointing to. Okay, where it is pointing, it is null. There is no data there. Okay, so basically it will say there is no data here. You first give some data. You first let it point to the address of some integer, character, whatever it is, point it there. Then you dereference it. Okay, so both these lead to errors due to different reasons. All right. So yeah, so that is pointers. Basically, we will spend maybe some more time on pointers in the next lecture before we move on to structs. But you have to read up a lot. At least you read the handout I posted on Euclid along with the previous lecture. I posted a pointers handout also. Go through that, you will understand most of the things I am saying. Okay. So any doubts? All right. So if there are no more doubts, yeah. Tell me.
Like memory
Sorry.
regular method.
Sorry, memory.
Sir, for memory consumption, is better pointer or like the regular method?
For memory consumption, which is better, you are saying?
Yes, sir. Pointers or regular like functions kind of.
Arrays. You see, memory consumption, it's not like that. It depends on the problem. Like if you want to deal with linked lists, you necessarily have to use pointers. If you are dealing with arrays, you are using pointers at the background, but you need not be conscious about it. Okay. If you are dealing with any large data type, whether it is arrays or linked lists or trees, anything, you are dealing with pointers. Usually, whenever you can use arrays, use arrays. If you necessarily need to use where arrays are inefficient, where your memory is quite dynamic, your data size is increasing, growing, you're adding some elements, deleting some elements, you're constantly doing this adding and deletion, then arrays are not good. Then you go to linked list. There you have to use pointers. Okay.